Our next presenter is Dr. Calvin Wang from Oklahoma State University. He is actually the Associate Director of the SPTC at Oklahoma State, one of our partner institutions. So Dr. Wang received his BS and MS degrees from Southwest Jiaotong and Beijing Jiaotong universities in the 1980s in China, and his PhD in civil engineering from Arizona State University in 1992. In the past 25 years, he practiced engineering at the Arizona DOT, conducted research and taught transportation classes at the University of Arkansas and Oklahoma State University, and he is considered a world leader in automated pavement surveying, 3D laser sensors, and related technologies. So we are very pleased to have Calvin talking to us today about big data and pavement engineering in a changing climate. Following Calvin's talk, after a few questions, we'll exit back to the atrium for some refreshments and then some final remarks. So please join us afterwards. And thanks. Calvin?
Thank you, Jerry. Well, it's an exciting day to sit here listening to climate scientists talking about how those factors, weather factors, can impact engineering. It's been a long time for me to sit in a conference that's not directly related to what I do, and so learned a lot. The good thing is Dr. Mike Meyer touched the subject engineering, and I'm the last speaker, so I'm an engineer, so I'm going to actually talk about engineering problems and solutions in my field. I would like to alert you guys that I'm not a climate scientist. I don't have training in that area, so I learned a whole lot today. So the materials I present to you are still civil engineering issues, but they are related with temperature, for example, and moisture, and among other things. So I'm going to talk about big data and pavement engineering and what we've done in the last 15-some years in two subjects primarily. On the design side, for people who work in pavement area, we know that the U.S., at least many states, are moving into the direction of mechanistic empirical design process, and it's a very big shift. Not all the states are following, but many are. So I'm going to address the big data issue regarding the new design process and how they are relevant with climate change. And the second aspect I'm going to talk about is pavement survey. Okay, we just had a climate scientist talking about engineering design. We need data, and we need lots of data. And we are able to collect the data now, okay? And then how to process the data, how to store the data, regarding pavement conditions. The third item that I'm going to just touch kind of very briefly is the materials performance. Unfortunately, materials performance relies on climate factors a lot, okay? I say unfortunately because I'm not a materials scientist. I'm not even a pavement materials engineer. So I'm going to stop right there. I'm going to just talk about essentially two issues here. One is the traffic data in the next generation design, The second one is the distress survey, how the new technologies can be used to collect, archive, and process the information. So the focus of the presentation is essentially regarding new technologies for payment design management, okay, and what kind of relevance they have to the climate. Now, first, let's talk about payment design. The existing design most states use today is based on the 1993 AASHTO guide. And that guide has many limitations, okay? The biggest limitation would be how traffic loading is used, the data is used in the thickness design calculation. For those that are familiar with this design process, essentially we convert all the traffic loading from passenger vehicles, pickups, full-size trucks, 18-wheelers, and everything else into a standard easel. 18 kips axle loading. And it's very logical and relatively simple. However, that kind of a concept has many limitations because the data is way, way inaccurate, okay? And of course, there are other limitations of the existing design process. I'm not going to go into too much detail because, as I said earlier on, the first part of my design focus is on the traffic side. As you can see that this current design handles roughly 2 million easels. But again, as we go on, our loading increases drastically. And even for the magnitude side, the current design is not efficient. Roughly 15 years ago, there started a national effort saying that, hey, the 93 design guide was useful, but it has so many limitations. Let's start with something brand new. Okay, this brand new is this system design of this new process. We have climate that impacts materials, as I said earlier, traffic, okay, structures, and how the payment responds to climate, materials, traffic, and everything else. And then, of course, the damage model here and how we can figure out what the distresses will be in the future. So as you see that this was documented roughly 10 years ago. There are many advantages, okay? The biggest advantage, I'm not going to read the whole slide. The biggest advantage of the new design process is people started all over. They essentially said, okay, here's what science says, okay? Here's what the mechanics engineers or scientists would do or would think. Let's start from the science side. Let's start with the loading first, the damage model first, and how the loading would cause the new strain-stress relationship and how that relationship can really become the damage model, as we know that the payment deterioration is not caused by passenger vehicles, it's really caused by big trucks, okay? And how that process can be modeled accurately. So that's the biggest issue in the new mechanistic and empirical design process. And then it incorporates many transition functions, such as we can predict roughness and various types of distresses like rotting and cracking. Another important thing for the new design is a tool for forensic analysis. For example, if you have temperature change, you have a moisture change, for example, rainfall change, you can easily tune this new design process to figure out what kind of information you can get out of that. The cumulative design approach, which is extremely important regarding the loading and the damage, etc. For example, we consider traffic, hourly traffic, season, and growth over time, and everything else. This is just a screenshot of the software, which is made by a company called AIA. Actually, it's owned now by AASHTO, which you can license, paying a license fee to use it. There are three main categories of input for the new design process. We have traffic, which is very, very, very important, as we see here, climate. That's what we're here for today's conference. Of course, structures by itself, including materials properties. And then there are three design levels. The level 1 is site-specific. Level 2 is more like kind of statewide or regional, and the level 3 is more like national default. Okay, why the 93 design guide have issues, right? Equivalent single axle loading, as mentioned earlier, ESO, okay, that particular number is a single number that it essentially tells you how much traffic loading this pavement will experience in your design cycle. You say it's 10 years or 20 years or 15 years. And so that's a standard 18 kip axle loading there. And it's based on a single equation, the entire pavement design process. When you look at this, this is essentially the loading 18 kips ESO number, and then you have various parameters in there, including structure number, pavement layer depth, and serviceability values, and many other numbers. Now, this is essentially a single function that it can do the whole thing, and a lot of people still use it today. In the ME design, essentially, you have to look for a lot more detailed information regarding traffic. For example, ESO goes away in the new design process, and the traffic input will be axle load spectral based. Essentially, you have to tell what kind of vehicles you have on your road and how many axles that vehicle has regarding configuration and what is the loading for those axles. This is a typical example. You have buses, you have pickups, you have those concrete trucks, and you have other haulers, and then you have 18-wheelers there. And then, similarly, traffic level inputs also have three, 1, 2, 3, and the level 1 is the most accurate site-specific. I'm just going to show you some slides, and then I'll come to what we've done with our research. See, hourly variation, 24 hours, and each hour has different level of truck volume in this particular case. And daily volume, class 9. Class 9 is the traditional or commonly used 18-wheeler. As you can see, they have big variations regarding volume on a daily basis. Monthly variation. As you can see, in the summertime, we tend to have more truck traffic than the winter times, and the annual evaluation as well. Annual evaluation. Now, this is the so-called load spectra, and that's what the new pavement design guide uses. This is just illustration of a set of data, okay? And when I tell you later how much data we really work with, it's a lot more than that, many magnitudes than this. Now, when I say we need to know the type of vehicles on the road, and we need to axle configuration, we also need to know the loading on the axles, and how do we find that out? Can we send people just waiting there to count, or just use the weigh station on the highway side to do that? Or do we have a better technology? And actually we do. The transportation planners have been relying on a technology called weighing motion, WIM, we call it WIM, for a few decades. So roughly 15, 20 years ago, pavement people, they said, okay, you guys are already using the technology. We can rely on the same thing to figure out the truck volume, axle configuration, and axle loading. And that's exactly what we're doing today, okay? Traffic monitoring guide. There's a guidebook published by Federal Highways and is used as the baseline to qualify the data from those WIM stations. For those who had any experience with WIM, we know that WIM sensors produce lots of errors. Okay? When the WIM sensors provide inaccurate data, what do? You try to get rid of the bad data and try to return the good data. And that's what we did here. We developed a technology called PrepME, which essentially is a preparation software program to prepare data for ME design. And this particular project was initially funded by Arkansas DOT and later on by Federal Highways and 8 other state agencies, and it became a proof-of study. So essentially, it's a software system that we designed and we made that can help users to prepare data, not just traffic, other data sets, including climate data, so that pavement designers can use this software program as a resource or as a tool to help them to use the actual ME design guide in the actual engineering exercise. So we use the essentially, we use the TMG format, which the first version was released in 2001, and now we use the 2013 format. And the TMAS is another system that developed by Federal Highways to check traffic data quality from WIM sites, and we use that as well. And it's very robust SQL server-based system. And I'm going to go through this input quickly, but I'm going to show you this. This is our data qualification software for WIM data for the pavement design. As you can see that there are 2 picks. Why there are 2 picks? One is loaded, the other one is not loaded trucks. And as we know that 18-wheelers do the most damage, the vast majority of damage to the pavement. So this is just an example of 18-wheeler Class 9 trucks, the data quality that we were seeing here. If you got the data from WIM site that goes like here or stops like here, which means either the WIM sensor was miscalibrated or is bad. Okay, so we use this software to automatically check if the data from your WIM sites is good or not. Anyhow, the TMG QC, we use that. We use daily sampling, monthly sampling, and we have a whole bunch of copy and paste functions and manual processing to accept or reject data into the process. And then we generate the traffic load spectra for ME design. We currently use the North Carolina DOT's clustering method, also Michigan DOT's method, Kentucky's method, and TTC's method, and a simplified TTC. Both are already built into the ME design, and for essentially to refine and prepare high quality traffic data for the design process. This is just one visual of the load spectral output that you can use for the ME design process. I mentioned earlier about clustering, which is very, very important for those people who study statistics. Clustering essentially is a methodology to gather your information from the big data or from the population, trying to find a pattern from your population that can fit your particular site. And that's exactly what we were doing for the traffic data. When you design a pavement section on a specific site, you want to estimate as best as possible the traffic loading and pattern for your particular site. That's what the clustering does here. Climate data is very, very important, and it's not because we're in the climate conference today, but it is a critical piece of information that we can import for several national data sources regarding essentially the rainfall and temperature on hourly basis, on daily basis, so that we can incorporate all those information into the design process. Okay, now, the title of the presentation starts with big data. Okay, what is the big data? I mentioned earlier, the 93 design process or design guide by AASHTO only requires a single value for traffic loading, okay? That's called EASL, either 2 millions or 1.5 millions or whatever that is. In this new design process is a complete different picture because we're really looking at hundreds of gigabytes for the extended period of time for a DOT. Hundreds of gigabytes, guys, instead of a 2-byte value. So that change is huge. It's not one magnitude. It's many, many magnitudes, okay? Then the next thing you need to worry about is data management, data qualification. That's exactly what our software does for this. So that essentially finishes the first topic on payment design, on what we've done in the last 5-6 years in developing this technology to help state agencies prepare data for the next generation payment design system. Now, big data for payment distresses. So switching topic to payment data collection. As we know that payment distress or distresses and the profiles are all very, very important for payment management, also for design. As we know that in the new ME design process, it requires historic data for calibration purposes for roughness, rotting, and cracking. Now, in order to know all those information, we have to gather data. Right now, the dominant data resolution to examine payment surface quality is 1 millimeter. Okay, we want to know that 25.4 millimeter is an inch. And then the new technology today is 3D. I'm going to show some of the 3D technologies we developed in recent years. And then number 3, when you have all this kind of data, how to process those data and have trust in your data for acceptable precision and BIOS levels. And that's extremely important and also very, very difficult. For those in payment area, Federal Highway is leading a proof-on study. It's going to be a multi-million-dollar study just for distress. It's just recently started. So that's a very good news because we have not spent serious resources on this particular topic. Now, big data for payment survey, right? How big we're talking about? Is that big data? It is very big. I know some of you here probably also do some traffic or ITS, and it also involves big data in these days. And I can tell you that you haven't seen this value here. I'm talking about 10,000 lane miles, okay? That's a very small DOT. If one DOT tells you that they have 10,000 lane miles, that's a very small DOT. I even do not know if there are states in the US that only has this lane miles. I think ODOT has several times more than that. Arkansas has also several times more than that. When you go to Texas, you time 10. They have 100,000 lane miles. So you have to multiply with whatever the value you have to this, and that will be your end result. And that's tremendous, tremendous amount of data. So it's a huge, huge challenge, even for today or next couple of years, computer technology to archive the data just for one, okay? Now, this is our new technology that we developed through the years. First, when I was in Arkansas, and recently at OSU. This is the vehicle we just put together this summer. This is our second 3D vehicle for R&D purposes. Yes, you probably can see vaguely something shining on the ground, kind of greenish. That is called the green laser. We started using green laser, and when I showed this to a guy from Sweden, he was real happy. He said, we're trying to work in the German market, and in Germany there's a law prohibiting using invisible light, laser light in public. So if you're using the infrared laser or near infrared laser, those kind of lasers are largely invisible. That's all other guys are using today you actually cannot use that kind of device in public area in Germany. So that's very interesting to know. Essentially, this vehicle can scan the road at highway speed, 60 miles an hour, across roughly 14 feet wide lane, and at 1 millimeter resolution with 2 sensor boxes. So we are able to work on highways, and we are able to work on airfields as well. I have some visuals to show you. This is an example that FAA obtained this technology from us, and they're on the runway ready to do a test. And this is the visual that I have for you. We collected a couple years ago on I-35 going from Stillwater to OKC. As you can see that this is the original concrete surface, and it deteriorated quite a bit along the joint. This is the close-up, and that's the quality we're going to get at 60 miles an hour, complete coverage, roughly 14 feet wide, and every millimeter, every pixel, every millimeter, we have data point. And that's the big data we're dealing with today. And the big challenge, as I told you earlier, is how to process that kind of vast information real fast, very efficiently, and accurately to get the results you're looking for. So right now, the sensor technology is very, very good, is completed, and then the main thing is, the challenge is how to provide solutions to users. If you do a quick calculation, if you drive at 60 miles an hour, every second, you have roughly 28, 29 meters. Okay, that translates to roughly 30,000 lines, 30,000 millimeters. That's how we design our sensors to handle this kind of speed. Remember, this speed is not just a point, it's a line. Okay, so every second, I have 30,000 3D lines. Each line is about 14 feet wide or 40 feet long, essentially transversely across the pavement. So every second, I can get 30,000 lines out of the sensors at that speed. So this is the visual that I showed you earlier on. Here's another visual on the I-40 bridge in Oklahoma. I'm going to show you some visuals on the runway we surveyed this year. It's a full-size runway, concrete, and it was not open to traffic. So they asked us to go to take a closer look, and we did. This is a visual. We use our 3D system. As you can see, they have a utility cover here on the runway, and you guys notice what this is? Looks like somebody kind of grinded it, right? That's exactly what they did. They used they probably went to Home Depot or Lowe's and bought a grinder. They manually grind it off. Okay, I'm going to show you why they did that. Brand new runway, $30 million. You see the problem on the runway surface here? It's not even. So essentially, the big contractor, they hired a rookie engineer to be the supervisor for 3 months to lay the runway. And the guy probably, when they took a lunch break or whatever break, they forgot to turn the machine off. So that's the quality you're getting when people are not experienced and trying to do a big project there. And our machine is able to detect those variations. Another thing is, you said, okay, runway is so wide, right? Runway is about, the full-size runway is about 150 wide. 150 feet wide. And how do you use a vehicle which covers only 14 feet to survey the runway? We do have a trick. We actually develop a software that can, we run our vehicle back and forth, like 20 times or more. And then see those data passes? Each pattern is a pass of the vehicle, okay? When we got the data, we're able to stitch them together so they do not overlap. So this will be a complete runway. This actually is the starting point of a runway. And we have a software actually can stitch them together and do PCI analysis from there. Okay, this is a visual that we did with a 3D surface of the runway. And the Boeing, this is runway longitudinal profiling, which is very different from highways. In highways, we use III. On our runways, they call it Boeing bump methodology, and it's very well defined in the FAA advisory circular. And those are just some visuals we developed, figures we developed for this particular airport. Boeing bump index there. Okay, I'm toward the end of my presentation. I'm going to show something kind of fun here. We have seen grooves before, right? Some people call it tines or tinings on highways. On runway or airfield, we call them just grooves. FAA has very specific definitions of the depth, the width, and the spacing of grooves. But even today, there's no technology to measure the performance of the grooves in the field. Okay? FAA said when you construct your runway, you put your grooves on, and that's the specification. You follow that, then you're okay. And it has specific tolerances here, if it's good or not. See, this is the new runway's grooves. As you can see that, it's not even, all right? This one is even worse. See the grinding here? That's from our 3D data. And see the problem here and everything else. We have a software essentially to evaluate groove performance. We exaggerate in the vertical scale so we can have better visuals on them. And then we see areas that are out of spec on the new runway. We can do cross-section measurements, okay, and cross slope. I'm going to stop showing the data, but I'm going to talk about briefly, maybe for a minute or two, regarding a new computing technology we're using in the lab now that is using GPU and parallel computing to handle the massive amount of data. We're really dealing with terabytes and terabytes of data at one time. Okay, how to load the data, how to save the data into memory, and how to look for defects into those terabytes of data sets. This figure came out of a company called NVIDIA. They showed the GPU performance is literally 1 or 2 magnitudes higher than the fastest CPU you can have today. Okay, for those guys who play Xbox One or PlayStation 4, that's what they use for the games. They use GPUs, and we're doing the same thing in the lab, trying to use parallel processing that can increase the performance by a factor of 10 for actual performance. And we've seen that, and we actually have products out there today to do the processing, relying on GPU. Okay, a little bit more visuals on the processing we have for cracking. Lastly, this is very interesting. I said earlier, the 3D laser system we have is 1 millimeter, right? We tuned the system to do 1/4 millimeter. This is on a bridge deck. Okay, this is the steel bracing on a bridge deck joint. We know that it's broken here. The deterioration is pretty severe, completely gone. This is the 1/4 millimeter resolution. As you can see that, it's very detailed, and it captures a lot of information for you. Right now, we cannot automatically to detect the deterioration level of the steel bracing on bridge joints. Okay, that's what we would like to do in next year or two. Another subject I didn't address, I literally don't have time. Jerry gave me 40 minutes. I think I'm very close to that. The rainfall on pavements or on runways, essentially water on runways, right? It's a safety problem. It's definitely related with climate issues. It's a big issue for runways and also for highways, okay? And we use grooves, we use tines on the surface of pavement, not to improve friction, okay, but to relieve the water as fast as you can from the surface, okay? And it's very, very effective, supposed to be. And then we're actually working with FAA right now and also Federal Highways. We have contracts right now at OSU trying to study rainfall intensity and the geometries of the runway and highway and how they develop water films and how those water films can impact traction of vehicles' tires or airplanes' tires. So that's something we are doing new. So you're going to see papers coming out from our group in next year or two. So, conclusions, big data, okay? Big data is buzzword from last year or so, right? A lot of people in the internet world, they talk about big data. In transportation area, we had big data long before they had internet big data. We are big data people, okay? So you're talking about ITS, connected vehicles, and payment engineering. If you want the gigabytes we have, you want the terabytes we have, and then next thing you know is petabytes. I mean, I have to look for Wikipedia for this word, and then exabyte, and I knew exabyte because there was a company called exabyte, and so on. So it's a very exciting and challenging world. We learned a lot here today from climate scientists. I had some doubts, Musharraf and Jerry, regarding setting up this conference to talking about not really transportation engineering, but something related. But it's just eye-opening to see what OU has been doing with climate research and other schools. And we are very, very fortunate to have OU to host SPTC, and it's a great center. We enjoy all the benefits of centralized funding for our partner schools. So appreciate that. And I guess that concludes my presentation.
I know I have a question, but I'm going to let you guys ask questions first if you have one. I see one here. Go ahead.
It was a nice presentation because you compared the as to 1990 design guide with the 2004 MAPD. So now as far as we are talking about the climate, so you touched upon those how traffic characteristics are incorporated in MAPD. That was really nice. I like you will agree with me, like the climate component of the MAPDG is the EIC. Right now the design procedure, what they do is they collect the weather station data from 5 nearby stations. So that the climate or weather data of the 5 nearby climate stations is older. Probably they are looking into the database of 20 years or 30 years back. But what other climate scientists were discussing today, we are looking at it. If we want to construct road, we should see what should be the trend of the data of the weather stations in next 20 years or 30 years. I think this is a particular area actually what we should work on. So I think you will agree with me, like in this presentation, we can also discuss or we can think like if we want to really incorporate the climate component, I think we should rather focus on the future weather data. What Catherine was mentioning that we have to look for the next day in the next future. So I think that can be added in the MAPDG. So that was my.
I definitely agree with you. The climate data is abundant right now. Any design guide has a default climate database that you can use. You said it right. It's really based on past performance, past climate data. But there are at least 2 climate databases that you can access, you can import into any design, but not by the any design software. You can do it by yourself. I believe Dr. Mike from NCAP was the last name, Mike at Heisman. Yeah, he has done a lot of work regarding importing the NASA climate data, which is actually more has higher resolution than the default any design database. I think there's another one. But climate data, I believe the NASA one may have the future prediction built in. We can look into that. It's a big area that Dr. Heisman, also Dr. Schwartz from the University of Maryland, those guys have done a lot of work just in the last 3 or 4 years. Yeah, I agree with you.
Wasi?
LTRC actually recently completed a study using the 18-wheeler for the structural value, any kind of structural coefficient, modulus or what you say. So we had to use that 18-wheeler. In the big data, what structural component you have, like any modulus or anything, because you're just scanning, right? So is there any structural like LWD or LWD type value included? You can extract anything out of that, or?
Well, I think I understand your question. The strain-stress relationship due to loading is very complex, okay? And then the current ME design software has that built in, okay? That part is, I think, is relatively mature. The immature stuff in the ME design software is not in the damage model itself. It's in the transition functions for calibration, like roughness, rotting, and cracking. And those three prediction models, either the models are bad or the data is bad, or both are bad. Because when you look at all the papers, they just like a shotgun. Regression results, just the R value is like 0.5, 0.4, that kind of data quality. So, yeah, so I think regarding 18-wheeler testing, I'm not sure who is doing that. I didn't quite catch what you meant by that.
Replacing FWD because it's kind of time consuming.
Oh, there's a highway speed deflectometer development going on. One device is from Greenwood in Denmark called the TSD. The second device is in the US. ARA has it. It's called a rolling wheel deflectometer. Those high-speed devices are very, very important for the future of pavement engineering. But right now, there's no conclusion. I believe people still have doubts regarding what those devices are exactly measuring. Are they actually measuring the vibrations or actual deflections or a combination of both? We don't know that.
So I had a thought when I was watching Kelvin's presentation. Years ago, I was involved with doing some pavement distress modeling for airports. And you look at families of curves and you look at distresses, over, basically you look at PCI versus years or age. And the models are not, they don't have very high regression coefficients, but that was sort of the state of the art. But when I was watching your presentation, I was thinking, there's a great opportunity to collect distress data over extensive miles of pavement, different types of pavement, different ages, and really look at the weather. We have such good weather data and develop some really good distress models based on weather and age. And then you could make some really good projections using the climate models looking into the future. So it seems to me that and that's just one idea, but there's tremendous opportunities to use this visual distress modeling and coupling it with weather and other things to really look at pavement performance. So I think it's very exciting. I see a lot of opportunity.
One quick question. The resolution in your 3D model, is it the same for both horizontal and vertical, or is it different?
The vertical is higher. Horizontal is 1 millimeter. Vertical is 0.3. Essentially, vertically, 3 pixels is 1 millimeter. So this goes against the GPS working principle. The GPS, the vertical is like 10 times worse, but ours is 3 times better vertically.
So actually, I think you talk about the MEP mechanistic design, but you know that actually it's not mechanistic. There's still a lot of empirical thing there. So I think one area that you did not talk about, like for example, serviceability index, PSI, and delta PSI. I think that would be one area. I think really the point that you made is definitely, but I think before that, I think let's say measuring PSI would be a great improvement to any DOT in terms of design, and then how the serviceability is changing. And climate definitely is a very important component in the changes in service.
Right, and for airport pavements, especially general aviation airports where the traffic loads are actually minimal compared to the environmental distress,
Right.
that governs the design. of
Yeah,
those
so
cases.
how do you measure number of cracks over an area physically? Here, you're automatically doing it, and your software is, analyzing it, the differences in the profile, right? So I think this is great, moving forward. But I think in terms of the climate particle, then I guess this integration would be also important, because a lot of things that happen to roadways are not all traffic related, but also climate related, and that's where the intersection.
Oh, yeah.
I totally agree with Dr. Miller and Dr. Zamang on the how to integrate the climate study with the pavement performance. First, the ME design, true. The second part, the ME design, the empirical side, is not very good. I guess we have graduate students here, they're actually in payments. You're talking about the next 10 years, so you make 20 years. Just a lot of opportunities to study that. I think, again, on the U.S., we spend a lot of money on payment research, but certain things we do poorly, versus like a province called Quebec and a small country called Denmark. And we do a little bit of research compared to those small places. This is another example, Jerry, is regarding like how to do the climate study on payments and collect those kind of data on a regional basis, like on South Plains. We go to Lubbock, Texas. We go to Dallas. We go to Oklahoma Prairie. We select maybe 50 sites. We do this kind of micro-size LTPP study. I think definitely it's necessary because the rainfall, the temperature, they just changed drastically in the last 10-some years.
Yeah, I see a lot of opportunity there. So if there's any climate scientists in the house who want to team up with Kelvin, I'm sure he would be. And that's what we're trying to do by having this event. So I think with that, we have a final break. And if you want to stick around and have some refreshments before you head on out, that'd be great. We do have some final comments by Renee and Mushroff. And so you're welcome to hang around and spend a little time talking with us. So we really appreciate you coming today, and we'll